Hi, I'm Sachin from the Faculty of Electrical Engineering, Mathematics, and Computer Science at Delft University of Technology. In this tutorial, we will discuss about the losses in a motor drive. We will first see the operating modes and how the losses are incurred in a DC motor drive. Then, we will take the example of the chip which is being used in the GEMS project DRV8411 by Texas Instruments and calculate the losses. Then, we will discuss the thermal management in semiconductor power switches. Let's first see the motor drive operation and the associated power loss mechanisms. We know from the lectures that the speed of the motor is proportional to the armature voltage. In a DC motor drive, this voltage can be controlled by changing the duty cycle of the switches. Both the half bridge 1, consisting of switches S1 and S2, and half bridge 2, consisting of switches S3 and S4, can be used to change the duty cycle. However, to reduce the switching losses, one of the half bridges is fixed to either a 0 or 1 duty cycle. If the duty cycle is fixed at 0, it is referred as low voltage, low side recirculation. If the duty cycle is fixed at 1, it is referred as high side recirculation. To calculate the losses, we consider high side recirculation in half bridge 1 as an example. The arrow in the figure on the right shows the current flow. The figure on the left shows the voltage at point 2 in the circuit. Initially, switches S1 and S4 are conducting. In this case, conduction losses are incurred in S1 and S4. Next, switch S4 is turned off. As the motor current cannot become zero instantaneously, it circulates through the body diode of switch S3 during the dead time. During this interval, the losses incurred are conduction losses in S1, turn off switching loss in S4, and conduction loss in diode D3. After the dead time, switch S3 is turned on. During this interval, the losses are the conduction loss in S1, switch turn on losses in S3, and conduction loss in S3. After the duty cycle time is over, switch S3 is turned off during the dead time. After the switch S3 is turned off, the current can only flow through D3. The losses incurred in this interval are conduction losses in S1, turn off losses in S3, and diode conduction losses in D3. Lastly, after the dead time is over, switch S4 is turned on. The losses incurred in this interval are conduction losses through switches S1 and S4, and switch turn on loss in S4. After understanding the loss mechanisms in an H bridge, let's consider an example of the IC used in the GEMS diamond board. The DRV8411 consists of two H bridges. The two H bridges can be controlled independently and hence can drive two motors if needed. In this application, the outputs of the two H bridges are connected in parallel to reduce the losses. Identical PWM signals are supplied to both the H bridges. In this slide, the various parameters necessary to calculate the losses are collated from the datasheet of the IC. These are shown in the table on the left. Furthermore, operational condition where the losses are calculated are shown in the table on the right. Let's first see the distribution of the conduction losses in the switches. In the first half bridge, conduction losses occur only in the switch S1 as it is conducting for the whole duration. Also, as the duty cycle is zero point 0.5, same conduction losses occur in switches S3 and S4. The factor zero point 0.5 is applied to all the losses as there are two switches in parallel as shown in the figure on right. As seen in the previous slides, for this particular case, the switching losses occur only in switch S4. These are calculated as shown in this slide. Similar to the previous case, the diode conduction losses occur only in diode of switch S3. Hence, these are shown in this slide. Other than the main losses calculated above, there are also some negligible losses that occur in the motor drive. These are the gate driver losses, device standby consumption losses, LDO regulator losses, and so on. After calculating the losses, we need to create a thermal dissipation strategy. For this, we need to understand what are the mechanisms of thermal dissipation in an IC. The figure in this slide shows the three main heat dissipation mechanisms. These are conduction, convection, and radiation. Generally, in ICs, majority of the heat is first transferred through conduction to a large surface area and then dissipated to the environment through either convection or radiation. This slide shows a simplified steady state thermal circuit network. It can be seen that there are several entities between the junction of the IC, where the heat is generated, and the ambient atmosphere, where the heat is dissipated. These entities impeding the heat flow are referred to as thermal resistances. The IC manufacturers usually provide several of the thermal resistance values in the datasheet. The various thermal resistances for the DRV8411 are shown in this table and are collected from the datasheet. After calculating the total power loss in the IC, we need to find the temperature rise from the ambient temperature. This can be done by multiplying the thermal resistance with the power loss in the IC. However, it is the designer's responsibility to decide which values to use as per the heat dissipation strategy. Furthermore, some parameters such as the R theta JA are not applicable as they are calculated with certain conditions which are different from the real application. In conclusion, in this tutorial, we discussed the operating modes of the DC motor drive and the power loss mechanism in the converter. Thereafter, we saw how the DRV8411 IC is used in the GEMS diamond board and did a back of the envelope loss calculation for it. Lastly, we discussed the different heat dissipation aspects for semiconductor ICs. This concludes the tutorial. Thank you very much for your attention and good luck with the rest of the study.